Okay, so if we're following the same format from last time, what we would do is we would call the inside of this, we call it, let's say, theta. In other words, we're saying that theta is equal to the angle that comes out of this inverse trig function when you plug t into it, right? And then what we're really looking for then is arc cosine of theta, right? That's what we want to know. Okay, so anyone have any ideas of what we could do here?
I did the chain rule, which...
So is this one, hold on, I need to look at the instructions. Did this just want the derivative? Hold on.
Yes, I believe so.
Oh, we just find the derivative. I'm sorry, I thought they wanted to convert that to an algebraic expression. My fault, sorry about that. My apologies. We could convert it to an algebraic expression, but that's not what they want. Okay. All right, so we're going to have to use some chain rule, right? So we have arc cosine of this junk here, right? Junk. So the derivative of arc cosine of anything, right? We have this on our formula sheet. The derivative of arc cosine of x should be -1 over the square root of 1 minus x squared. So that's right off our formulas, and that we could have got from last time. I think I have it right here. Yeah, let me just grab that, copy it, and bring it over here real quick. So I'm just using, I got a cramp. I'm just using that formula right there. So that means the derivative of this should be -1 over the square root of 1 minus. Now this time it's not x, it's the actual junk. So I need to put arc sine of t, but that entire quantity, I'm going to put in brackets, that entire quantity squared. And then we say times, now we do chain rule, now we need to take derivative of the actual inside the junk. And the derivative of arc sine of t, we're just going to use this formula, but use t instead of x. Or, yeah, t instead of x. So 1 over the square root of 1 minus t squared. That's pretty much it. Not a whole lot more you could do. I mean, you could try and combine those roots together, but I think that's sufficient. Does that answer the question?
Yeah, that's what I got. I just thought it was too easy. I thought I did it wrong.
Oh no, that's it. It just looks ugly, but it's right. Okay, you want me to look at 6 also?
6, yeah. I couldn't get that one. The ln was really messing with me.
Okay. Let me just copy it real quick. And I'll leave my formulas up there. There we go. So same thing here. We need to take derivative. So what we need to realize first is that there's multiplication right there. And that means we're going to have to do a product rule. So if we do a product rule, we're going to need to start by, I'm going to write this a little different than I did last class. It means we're going to have to start by taking derivative of the first function. So we have to take derivative of x, multiply that times the second function. I'm going to write arctangent this way instead of the other notation. And then we'll add to that, so this is product rule, the derivative of the natural log part times the x. So this goes back to Cal 1, and there's something I want to just mention here about this. When you look at the formulas, I don't want to take too much time on this, but when you look at the formulas right here, let me zoom in on this. Okay, so in Cal 1, where's the product rule? Okay, let's look at the product rule first. So the way they teach this, or the way it's taught in the textbook, is that you do, let's say f is our first function, g is our second function. they teach you to leave f alone, take the derivative of g, then add to that, leave g alone, and then do the derivative of f. So another way that I could write this is if you have f times g, the book says to do f times g prime plus g times f prime. All right? Everyone okay with that? Now, if you look at the quotient rule, which is right here, number 6, they say if you're going to take the derivative of f over g, according to the book, they teach you to do g times f prime minus f times g prime, and then all of that over g squared. And people learn it different ways, right? I mean, there's even cute little acronyms that you can like sing a little song and stuff. But I actually don't teach it either way here, okay? Let me show you how I teach it. And that way, when I'm taking the derivative using the product or quotient rule, you'll understand why I'm doing it this way. And I'm not trying to get you to undo what you've learned, but I think when I write down the way I do it, you might understand why I do it this way. So the way I teach my students is I say, if you're going to do f times g, then it's going to be f prime times g plus g prime times f. Okay, so the only difference is I do this one first, and I commute it, so I flip the order, and then I do this one, and I commute it and flip the order, right? So it's like, big deal. Why'd I do that? Well, because if you look at the quotient rule now, then the quotient rule, the way I teach it, is f prime times g minus g prime times f over g squared. So can anyone tell me, just by looking at that, why you think I might teach it that way instead of teaching it the way the book does it?
Just because they use the same setup in the numerator?
Yeah, exactly. Because the way, when you learn it the way you learn it in the book, and I can remember being a student learning it this way, to me it seemed like two completely different formulas that I had to memorize. Whereas with the way that I teach it, really all you have to do is memorize this part, because it's the same in both the product and quotient rule, except for the minus between them, right? And then dividing by the g squared. So for me, in my mind, it's less information to have to store. So I always teach it that way. So right now I'm doing this problem, and I'm doing the product rule. I'm using this yellow one right here. So I just wanted to let you know that's why I'm doing it. If you can memorize f prime g plus g prime f, then quotient rule comes pretty naturally right after that, f prime g minus g prime f over g squared. Okay, so that's the rationale behind why I'm doing what I'm doing. And let's get back to the notes. Okay, so what you see here in front of you is, you know, this was the f times this was the g. Zoom in one more there. And then so this is saying f prime times g plus g prime times f. Okay, so that's what I'm doing. All right, so now let me just go ahead and do these derivatives. The derivative of x with respect to x is 1 times the natural log of arctangent of x, and then plus, now we have to take the derivative. Oh, I forgot my derivative mark here. Oops, sorry, right here, I should have put derivative right there. I'm going to be taking derivative of that. I just forgot to put it. I put it on the one on the x, but I forgot on the other one. Okay, so I need to take derivative of natural log of something, right? So my something inside is this thing. So this is composition, so chain rule. The derivative of natural log of anything is 1 over whatever that anything was. Now chain rule says times. Now I take derivative of the blue part, and the derivative of arctangent of x is the formula here. So that's going to be 1 over 1 plus x squared. And then I have to remember I have to do the times x to finish off the product rule. And that's it. I mean, you could maybe put all this together. You can maybe slide that x on top. Maybe you want to write it this way. Kind of put the denominators together with multiplication. And then have, you know, this same thing right here. And that's pretty much it. Is that good?
Sir.
Okay. All right, good questions. All right, let's get going with today's stuff. And then if there are more questions over homework or anything like that, just maybe we'll have some time at the end of class. Don't forget also, I'm available before class from 10 o'clock to 11 o'clock in my office hours. So I was just here like for the previous hour before our class. Nobody showed up. That's okay, you're not hurting my feelings, but I'm just letting you know I'm there. And then, do I have office hours today after class? I don't know if I do. I actually don't know if I do. I forget. Well, I don't know. I'll look. If I do, then I'll be there. All right, so today we're going to start 3.6. We're going to finish 3.6. It's a pretty quick section, and then we're going to get into antiderivatives after that. So this is our last section from earlier in the book, where what we're doing is we're introducing another 6 trig functions that you've never really looked at before. So we have right now our 6 trig functions that we're familiar with from pre-cal, you know, sine, cosine, tangent, all those reciprocal functions. We know their derivatives. Last time we talked about the inverse trig functions, right? Arc sine, arc cosine, all those. And then we talked about their derivatives. Now we introduce a whole new set of trig functions called hyperbolic functions. And these are very strange, okay? Because they're not based upon the unit circle, and they're not based upon right triangle trigonometry like from pre-cal. The definition of a hyperbolic trig function comes from exponential functions. So I wanted to start by showing you a visual of what these functions kind of look like. And let's see, this is going to be a little complicated here. Let me just get rid of this. This is just in the way. Yeah, okay, so what you see in front of you here is e to the x, all right? So we're all familiar with e to the x from college algebra. It's the natural exponential function, and we learn in calculus that this thing has some really good properties. Does anyone know what like the most important property of the exponential function is? It's from Cal 1. I mean, what is it that we learn about this function in Cal 1?
Isn't the derivative the same?
Yeah, so there's something about the derivative and the function being the same. And what we're saying here is this. We're saying that if we were to come to some arbitrary value of x here, and we were to go onto this function and take the height of that function. So, you know, I don't know, I went to about 1.2, right? So if I get on my calculator and I plug 1.2 into my calculator, so if I do e to the 1.2, see what I get here. E to the 1.2, I get 3.32, somewhere around there. So this is about 3.32. Okay, great. That's just plugging numbers into a function. But the thing that makes the exponential function so great or so unique is the fact that if I take the slope of the tangent line there, so if I actually look at the tangent line going through here, right? And I ask myself what the slope is. Well, the slope is actually equal to the height of the function. So the slope would also be 3.32. And that happens at every point on the exponential function. The slope of the tangent line at a given x value is equal to the y value of the function. And there's no other function out there that does this. This is the only one. It's unique. In fact, it actually works the other way around. We were looking for a function, we physicists, chemists, biologists, we were out there looking for a function like, is there a function that has a property? So we were looking for, we're saying, does a function exist out there that when you take its own derivative, you get the original function, like nothing changes. And we were looking for it, and we discovered that the only one that does it is this one, e to the x. And so it just kind of naturally occurs that this is it, right? And it's unique. So it's a very special function, and we should all be familiar with it, all right, what it looks like. So that's e to the x. Now I'm going to show you another function, which is e to the negative x, which is a reflection of that function over the y-axis. So it's like you could say that e to the x is an example of exponential growth, and the blue one, e to the negative x, is an example of exponential decay. Now we're going to do something very interesting. We're going to take these two functions and we're going to add them together. Okay, so that means that, like, if I go to, let's say, if I go to 0, right, and I go in, both of those functions have a value of 1, right? So if I add those together, 1 plus 1, I get 2, right? So we're going to add the two functions together, and then we're going to divide by 2, right? Don't worry about why we're dividing by 2, but just that's what we're going to do. So we're going to add them together, which gives us 2, and then we're going to divide by 2, which gives us 1. Okay, so now I'm going to have a new function that has a y value of 1. And then what we'll do is we'll go out, let's say, to 1, and let's add the two functions up also. So that means I'm going to take the height of this one and the height of that one, add them together, which will make it a little bit taller than the red one, and then divide by 2 again, which should throw me a point somewhere around here. And we do that the whole way, to the left and to the right. We keep doing that. And when we do it and graph all the points, we get that function. Oh, I did that pretty good, didn't I? Okay, so that's a new function. And you may be like, well, you know, what's so important about that function? Well, it turns out, again, that in physics and engineering and different math applications, this e to the x plus e to the negative x over 2 actually, like, naturally turns up in a lot of problems. And turns up so often that we said, you know what, since this expression keeps on turning up, let's just call it something. And that is actually the hyperbolic cosine function. All right, that's what it is. Now, if we take, remember how I said we take the two functions and add them and divide by 2? What if we take the e to the x, subtract the e to the negative x, and divide by 2? That, again, occurs a lot in different applications. When we do that in graph, we get this function, this kind of orangish looking one. And that one is our hyperbolic sine function. And then the hyperbolic tangent would just be the ratio, sine over cosine, hyperbolic sine over hyperbolic cosine. And then all of the other 3 would be all the reciprocals. Okay, so I just wanted you to kind of see them and before I start getting too much more into the notes. So this is our actual definition. Let me see if I can remember how to do this. Yeah, that worked. Okay, so here's our definition. Sine with a little h next to it is called the hyperbolic sine, or you can say hyperbolic sine, or you can say sine hyperbolic, doesn't matter, of x is equal to e to the x minus e to the negative x divided by 2. Or you can pull the 2 out front as a 1/2, and then you can really see clearly, I think you can see clearly there, that you have subtraction between the two e to the x's. Well, one's e to the x, one's e to the negative x. And then the cosine hyperbolic is the two functions added together and then taking half of them. So the way I remember it is that I remember e to the x and e to the negative x. And then the way I remember the plus and the minus, which one it is that the sine one, s, I always remember s subtract. That's the way I remember it. And then cosine is just not subtract. But however you do it, remember these are formulas. These formulas are in your formula or on your formula sheets. But you know, if you're trying to get these things kind of in the brain, so you don't have to always look at your formulas, that's the way you can remember it. And then you see that the other trig functions are just all just these things divided, right? Or ratios are flipped. So if you take this entire expression here and divide it by that entire expression, then you get the tangent hyperbolic function. And then the rest are just reciprocals. Any questions on that? Okay. So what's a good example of where these would come up? Now, normally if I'm in a classroom, I can do a really good demonstration here. What I do is I get up on the board, I get a volunteer, and we hold a string. And we hold it up against the board and we draw a curve on the board. And we look at that curve. So imagine a string right now, if you could, hanging. You could even imagine if you had two poles. And you hang a wire or rope or something between those two poles. Oh shit, okay, that's good enough. So if you hang a wire between those two poles and just let gravity take over, you get this curve, right? And the question is, you know, what is the function? What type of function would model that curve? And you may think parabola, right? Parabola seems pretty natural that might be what that is. Well, it turns out that it is impossible to come up with any parabola, okay? So, you know, with parabolas or quadratic functions, we have a lot of control over quadratics. All we have to do is change the A, the B, and the C, change those numbers, and that changes the shape of the parabola. It makes it wider or more narrow. We can move it up or down. We can reflect it over. So you might think, okay, well, if I make enough adjustments to the A, B, and C, I could get that hanging wire, a function to lay right on top of it. But it turns out it's impossible. You can't. Like, you may have a parabola that you draw here, and it might be really good down here. It's showing, like, it might just lay exactly on that wire, but then over here on the edges, it's gonna deviate. And so it's just impossible, all right? But there is a function that would lay right on top of that, and it's a hyperbolic function. And it turns out to be a hyperbolic cosine function. And so these are called catenaries. If you've ever heard that word, a catenary is a hanging wire. And the function that represents a catenary is A cosine hyperbolic of x over a plus c. So that's like the generic form of a catenary. In this example right here, what I did was I tried to show that if you have a catenary, here's a hanging wire, and then you try and compare it to a parabola, that it's impossible to get these two to lay on top of one another. Like, there's always going to be a little bit of error between them. And anytime you ever hang a wire, it will never be in the shape of a parabola. It will always be in the shape of a catenary. Okay, I think I made that clear. So you might be asking yourself, like, why would you ever want to know the function that represents a hanging wire? Well, there's a lot of things that you might need to do, right? Let's say that you are an engineer, right? And let's say that you're trying to figure out, think about power lines, right? You have these towers, and you have this wire hanging between them, right? And that wire has mass. And, you know, maybe if you took like 2 feet of wire, you put it in your hands, it'd be, you know, you'd feel it, right? It's there, kind of heavy. But if you take 300 feet of it, right? That's a very heavy wire, right? And you've got to suspend these from these poles. And when the pole, I don't think I'm going to have a good picture here. I'll just draw it underneath here. I don't know if you've ever seen this before. Showing my daughter this the other day, but when you have a pole and you have your wire coming in here, these wires are electrified, right? Like, you can't just connect it to the pole, or else electricity will just travel right down the pole into the ground. So you have to have some sort of insulator here that connects to the wire, and they usually use like these ceramic. You'll have to kind of look at a power line next time you see it. Next time you're out driving around, look at this. They have this ceramic insulator that connects to the pole, and then the next wire kind of like goes like this. So there's no path for the electrons to actually get to the pole because it can't get through the ceramic insulator. Well, would you agree that there would be one hell of a force on that ceramic insulator? I mean, isn't there a force, right, in that direction pulling? So your ceramic insulator must be able to hold this static load indefinitely, right? So you might need to know what that force is, and to know that not only the force, you might need to know the direction of that force, right? That, like, what is the pitch of that? What is the pitch of that arrow? It's not straight out, it's not straight down, it's to the side. So you actually might need to determine what this angle theta is. And to do that, what you're going to need is to find, at that point where it connects, you're going to need to find the slope of the tangent line to that wire. So you're going to need to know what the derivative of that wire is at that point. Does that make sense? Or the derivative of that function that represents the wire at that point. So if we have the function, if we actually have it, and we know it's a hyperbolic cosine function, then as long as we can take the derivative of it, we'll be able to determine the slope of that tangent line and therefore determine the force on that insulator. So I hope that all kind of makes sense. I'm trying to give you some value to what these functions are used for. All right. What else do I want to say about that? Nothing. We can talk about that more, but I'll just keep going. So the graphs, I already graphed these just a second ago. Here are your, well, I graphed cosine hyperbolic, which is that one. And then sine hyperbolic looks like this. Tangent is the reciprocal of those two, which turns out looking like that. Okay, and then how about the reciprocal of the hyperbolic sine? Let me get that one in there. Let me take these out. So there's, the red one is sine hyperbolic, and this purplish one is cosecant hyperbolic of x. So it's the reciprocal of sine hyperbolic, 1 over sine hyperbolic. Notice we have an asymptote, right? Because you can see that the sine hyperbolic goes through the origin, so it does take on the value 0. So 1 over 0 would never be defined. So the reciprocal function has an asymptote. Let me look at cosine hyperbolic. The inverse of cosine hyperbolic is secant hyperbolic. Will it have an asymptote? Is cosine hyperbolic ever 0? Is this function ever 0? No, right? So 1 over that should always be defined. So let's take a look at it. There it is. And then finally, we have the tangent hyperbolic function, and then the reciprocal of that is this. Okay, you don't need to memorize these. What I really want you to notice is that, you know, with like sine and cosine traditionally, pre-cal, like they look really the same. Like sine and cosine, the only difference between the two, there's like a phase shift, right? But otherwise, you could move them and lay them right on top of one another. But when you look at these, it's like they're all very different. None of these really look like any of our traditional trig functions. So I just want you to realize that. Okay, let's keep going. So in pre-cal, we establish what are the important identities, from pre-cal. And one of the most important identities from pre-cal is sine squared x plus cosine squared x equals 1, right? That's called the Pythagorean identity. And we learned that in pre-cal, right? And we use it all the time in pre-cal, and then it's peaked its head up many times in different, since then. Well, just like with the traditional trig functions, with the hyperbolic trig functions, there are some important identities also. And one of them is this first example that I'm going to do here, which is the identity cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. So notice it's not a plus between them. And with subtraction, the order matters, right? So it's the cosine hyperbolic squared first, and then minus the sine hyperbolic squared. So what I'm going to do right now is I'm going to verify this identity. I'm going to show you how you would prove this is true. And it's not hard. Cosine hyperbolic squared x minus sine hyperbolic squared x, okay, equals 1. Okay, so I want to show this, WTS. I want to show that this is true. So remember in pre-cal, when we're verifying identities, we always have to start with one side and turn it into the other side. You're not allowed to work with it like an equation because you're trying to show it's true. So which side do you usually start with? Do you all remember in pre-cal which side of an identity you start with if you're going to try and verify it? No?
The left side?
We'll do the left side here, but in general, what you want to do is start with the side that's more complicated, because then you have some way to go with it. If we start with the right side 1 and ask you to turn it into the left side, that's going to be really hard because 1 can go in many directions, right? So here's what I'm doing. I'm going to start with the left-hand side. So left-hand side is this, and I'm going to try and do as much manipulation to the left-hand side to make it turn in to the right-hand side. So first thing I'm going to do is I'm going to rewrite these using the definitions. So I'm going to go back over here up to the definition. So cosine hyperbolic of x can be replaced with that expression right there. So I'm going to do that. I'm going to replace it. So I'm going to put 1/2 e to the x plus e to the negative x. Now don't forget that's squared because we had the squared here, right? And then we're going to say minus, now we're going to have another thing squared here, but this time it's going to be 1/2 e to the x minus e to the negative x. All of that squared again because that one was squared. All right, and I'm going to hope that this turns into 1. So let's start squaring things. So I have multiplication here on that squared. So whenever you have multiplication inside something to a power, you can square each thing, square each factor. So I'm going to square 1/2. 1/2 times 1/2 is 1/4. I'm going to square e to the x plus e to the negative x. And I'm going to square that on the next line. Minus 1/4. So I squared the 1/2 there. Then e to the x minus e to the negative x. I'm going to square that. Okay, when we square those binomials, we actually have to do FOIL, don't we? Like when I do this step, I've got to actually like FOIL that out. So maybe I'll do that over here on the side. I'll do it down here. I'm going to do e to the x plus e to the negative x, and I'm going to do it times itself, e to the x plus e to the negative x, and then kind of just do my expansion. So what is e to the, oh, let's pick on people today. So I have from last time, I don't think I ever got to Christian, or no, Ross Christensen, Ross. Did I get you? If I got to you, let me know, because I didn't mark you down.
You didn't.
Okay, Ross. Okay, so I was going to just ask you if you could help expand this, just telling me what we have here. So e to the x times e to the x.
Would that just be like e to the x squared? Like just do another one, or would it be like e to the 2x?
Okay, so you're asking me, what do you think it is? I mean,
See,
it is one of those. You don't know?
It is one of those? Yeah.
Okay, so go back to this. If I asked you x squared times x cubed.
Okay, then that would be x to the 5th. So it's just e to the 2x then?
E to the 2x, okay.
Okay, cool.
Yep, okay, now what about this one? This one's gonna be a little weird.
Would that just be 1?
That'd be 1, right? Because it's gonna wind up being e to the 0,
Yeah.
right? So that's just gonna be plus 1. And then what about the middle one?
That is also 1.
Okay, so plus 1, and then plus
E to the
last one,
negative 2.
e to the negative 2x, right?
Okay, cool.
Cool, yep, that's right. Good. Okay, so that's what that green one is. So I'm gonna go ahead and write that down. That's 1/4. Then I'm gonna have to distribute that through e to the 2x. I'm gonna put those ones together if that's okay with everyone. 1 plus 1 is 2. There we go. Okay, so now I still have minus 1/4. Now, let's move on to our next victim. Participant. Let's see, I'm gonna call, Alexis. How about Alexis? Is Alexis here? I don't see Alexis. Okay, no Alexis. Okay, so I think I've called on everyone, at least from last time. So the system regenerated random numbers. So we're back to Maribel. So is Maribel here? Yeah, she's here.
Hello.
How's it going, Maribel?
I'm pretty good.
It's okay? All right, so what would be this next one? Like, what would be the big difference here if we did this expansion? We have a minus in there, right?
Yes, sir.
So what would that change? If this was a minus and this was a minus. So what would our first term be?
E to the 2x.
I can barely hear you, sorry.
E to the 2x.
E to the 2x, okay, and then what would be next?
0.
We're e to the 0, right? Which is going to be 1. But would it be plus or minus 1?
Minus.
Minus. So we have minus 1. And then the middle ones,
It will be minus 1.
minus 1 again. And then the last ones,
Plus.
plus.
To the negative 2x.
Good, good, good. Okay, good. All right, we're getting there. Let's distribute the 1/4 through. Yeah. So when I do 1/4, I got 1/4 e to the 2x. And then when I distribute it, 1/4 times 2 is a half. And then plus 1/4 e to the negative 2x. Okay, so I've distributed the 1/4 through the first parentheses. Now I'm going to just distribute a negative 1/4 through the second parentheses. So negative 1/4 e to the 2x. Putting those two together would have given me a negative 2. So when I distribute negative 1/4 through there, I get a plus 1/2. And then when I distribute the last time through, I get negative 1/4 e to the negative 2x. There we go. Do y'all see what happens? Yeah. So 1/4 e to the 2x cancels with negative 1/4 e to the 2x. What did I just do? What did I just do? I thought I disabled that. Okay, so the next one is the 1/4 e to the negative 2x cancels with minus 1/4 e to the negative 2x. And the only thing left is 1/2 plus a half, which is 1. So there it is. Now, there are many important identities when it comes to the hyperbolic inverse or the hyperbolic trig functions. We're not going to go through all of these, but to verify them, you would do exactly what I just did right here. You'd start with one side and you would use the definition, and then from the definition, you would show that it's equal to the other side. All right. So that's again, I'm going to put that behind us, and just remember that on your formula sheets, and this is not only this class, but just moving down the road in your life, you have your hyperbolic functions here on the formula sheet, right? They're right there. It gives you the definitions of them. I don't know if it gives you any of the identities. I don't see any of the identities. No, so you just have to know they exist. Okay. Any questions? We're gonna keep going. All right, so the whole point of this is first we just establish the fact that there are these functions, 6 new functions. And now we ask ourselves, what are the derivatives of these, right? That would be the very natural question that we would want to ask. So the derivative, we're just going to look at them first. The derivative of sine hyperbolic x is cosine hyperbolic x. That's just like it was for sine, right? Sine x derivative is cosine. So that lines up with what we've learned. But look at the derivative of cosine hyperbolic x. Derivative of cosine hyperbolic x is not negative sine hyperbolic x. It's just sine hyperbolic x. So you don't get that negative that pops up. It doesn't happen with the hyperbolics. And then the rest are here. And again, you don't have to memorize these. These are on your formula sheets. Just know that they exist. So what I'd like to do is I'd like to just verify one of these. All right. I just want to verify one. And let's take the second one, because that's the one that is not acting like the regular cosine function. So let's just see if we can just show how that is true. So I want to take the derivative with respect to x of cosine hyperbolic x, but I have no idea what it's equal to. Well, I know it's sine hyperbolic, but I'm acting like I don't. So what I do is I replace sine or cosine hyperbolic x with its definition. So that is the definition of cosine hyperbolic, right? It's 1/2 times e to the x plus e to the negative x. And now that I can differentiate because I took Cal 1 and I know how to differentiate e to the x. So this should be, let's see, the 1/2 here is a constant sitting in front of the function. And when you take derivatives, constants in front of functions just come for the ride. So 1/2 is going to be here. And now I can just take derivative of each of those separately because there's addition between them. The derivative of e to the x is just itself. Now be a little careful with this one here. Let's just go to our next person here. What's the derivative of e to the negative x Coleman?
Is it e to the negative x or negative e to the?
Negative e to the negative x. So yeah, you have to be a little careful there because when you take derivative of e to the negative x, it's itself, but then chain rule says you have to take derivative of what's up here. And derivative of that's -1. So you wind up getting negative e to the negative x.
Okay.
So I'm going to write this as minus e to the negative x. And do y'all recognize what that is? That is sine hyperbolic x. 1/2 e to the x minus e to the negative x. All right. Okay, so just quick recap. Pre-cal, you had 6 trig functions. We know their derivatives. Last class, inverse trig functions, we got their derivatives. So we're up right now to 12 derivatives, but today we introduced 6 more trig functions, hyperbolics, and now we know their derivatives. So now we're up to, what, 18? I can't do math. Yes, 18. We have 18 trig functions and 18 derivatives. All right, so this next example, where's my cursor? This next example is just, let's just see how we can now that we have these, let's see how we can implement a derivative of a more complicated function where we might have to do some product rule and things like that. So if we take y equals x secant hyperbolic of e to the x, and we want to find y prime, then Jane, is Jane around? I see Jane's name.
Yes.
Oh, there you are, Jane. Okay. So Jane, if you're asked to take derivative of this, what do you see as kind of like the big thing that we have to address in this?
Would it be the EX?
The what?
The EX?
I guess what I'm asking you is like, which of your differentiation rules is like the one that's at the foremost one in your mind that needs to be addressed?
Oh,
Like what operations do you see here?
the sec.
Secant hyperbolic. So are you seeing chain rule? Are you seeing product rule, quotient rule, power rule? What are you seeing?
The chain rule.
Okay, which part of it is chain rule?
The x times the
Oh,
sec.
you just said a word there. X what?
The x times the
Times, right? You said times, right?
time.
So there is a multiplication right there, right?
Mhm.
Which means that you have a product. You have a product right between those two things, don't you?
Yes.
Okay, so you should be seeing that you have a product rule as the big kind of thing you need to look at. Now, within that product, one of these is going to be easy to differentiate, the x. The other part over here is a chain rule. That's your composition. That's secant hyperbolic of e to the x. So that's a chain rule. But the chain rule lives inside of a product rule you have to do. So let's try and crank this out. We're going to take derivative, which means we're going to take derivative of the x times the secant hyperbolic of e to the x plus the derivative of secant hyperbolic of e to the x times x. Okay, so that's your product rule. Now the first one is just, derivative of x is 1. Plus, all right, so let me move on. I'm trying to get through everyone. Let's see, who's up? Jorge.
Yes, sir.
All right, now if y'all want me to call you something else, just let me know. Like if you have a different name that you want me to call you, I can. So Jorge, on the secant hyperbolic e to the x, you got any ideas on how to take derivative of that?
Would it be the formula says a negative sec x time?
Yep, so you're actually looking, yeah, sorry, I cut you off there, I apologize. Where's my thing? Why is it not working? There it goes. Okay. So what you're saying is you're looking at this formula right here?
Yes, sir.
Okay. Now we don't have x. What do we have? What is the argument of our secant hyperbolic function?
E to the x.
E to the x. So we're going to have to replace these x's here with e to the x's when we do ours, right? So you want to go ahead and tell me what that would be then?
So it'll be negative secant h e to the x times. Well, you have to do the
that, make it a minus. Okay. You said it's going to be negative secant hyperbolic of what?
to e to the x.
Okay, I'm gonna put it like that, and
Then tan
then
hyperbolic e to the x.
e to the x. Okay, a little bit more.
That'll be. Wouldn't that be it?
Well, what you've done is you've taken care of the derivative of the secant hyperbolic part.
Yeah.
Right. What you haven't done yet is taking derivative of its argument.
Wouldn't that be e to the x though?
That'd be e to the x. Good. And then you have to finish off the product rule, which means you have to bring this x in.
Times x.
There it is. I mean, that's pretty much it. We don't have to do anything else. I mean, we could factor out a secant hyperbolic of e to the x from both, but I mean, this is good. This is fine. We're fine just like this. Any questions? Okay.
Oh, I had a question.
Yes.
So after the tangent, tangent hyperbolic e to the x. How did you get the multiple?
Your audio is real choppy. I don't know if it's my end or your end, but I think what you're asking is how did I get the e to the x?
Oh, okay, it's probably me. I'm not sure.
Right. So
yes, the last part where it's e to the x times x.
So when we take the derivative of secant hyperbolic of something, the derivative is secant hyperbolic of that something times tangent hyperbolic of that something. Okay, that just takes care of the outer function, which is the secant hyperbolic. Then we have to go and take derivative of what's inside the secant hyperbolic, which means we actually have to take the derivative of that yellow thing. Well, it's green now, and the derivative of that is itself.
Oh, okay, yeah, I got it.
Just chain rule, right? Composition. That makes sense, Jimmy? Yeah, I'm not able to pick you up real good. Your connection's not that great. So okay. So what's coming next? We just introduced the hyperbolic trig functions, and now we have their new 6 derivatives. So what came after the 6 trig functions and their derivatives? Didn't we talk about the inverses of them and their derivatives? Well, guess what? All of the hyperbolic trig functions have inverses, functions that undo them. And so we're going to look at those 6, and then guess what? Each one of them has derivatives. So we're going to have now 6 new inverse hyperbolic trig functions and 6 new inverse hyperbolic derivatives. But that'll be it. We'll be done. So you have a total of 24 trig functions with their inverses and 24 derivatives. Fun stuff. Okay, now, this is always exciting. All right, so right now we're not talking about derivatives. We're just talking about inverse trig functions, or inverse hyperbolic trig functions. So here are the definitions of the inverse hyperbolic trig functions. Here they are. And there's something I want to point out here that's really important. Back when you're in pre-cal, right? When you're in pre-cal, you're taught, you know, that you have a function called sine x. And then you learn that it has an inverse, and the inverse of that function is arc sine x. So if we wanted to know, like, you know, what happens when you plug something into sine, we can do that because we just get on our calculators and we do it, right? But we understand that it's sine is the y coordinate on the unit circle at a certain angle. So like we have a visual idea of what sine is. And then the inverse sine, we talked about that last time. The inverse sine is just like going from the number back to the angle. So you can connect it within the circle. You can kind of get a visual idea. The thing about the inverse hyperbolic trig functions is that you actually have a definition. So if you want to plug a number into one of these, you just go and plug it in for x. So if I wanted to know what hyperbolic, the inverse hyperbolic sine of some number x is, all I have to do is plug it in here for x and here for x. So we actually have an algebraic expression for these inverse hyperbolic trig functions. We do not have that with the regular sine and arc sine. We don't. There's not a nice algebraic expression, but for here there is. So what I'm going to do is I'm going to actually show y'all right now where this actually comes from. Okay, and the reason I'm showing this to you is because we're going to do something. In me showing this to you, we're going to do something that you may have never seen before, and I think it's a useful thing to see. All right, so we are about to try. I want to show that the hyperbolic sine inverse of x is equal to the natural log of x plus the square root of x squared plus 1. All right, does it all make, or does it make sense to you all that there should be a natural log in this expression? Why would there be a natural log in this expression? Why do you think we would have that?
Because of the exponential function or the exponential.
Yeah, I mean, the definition of the hyperbolic sine involves e to the x. And so the inverse of e to the x is natural log x. So it should appear in here somewhere. Like that makes sense that it's there. But let's do it. Let's see if we can't show where this comes from. All right. So we don't know that this is true. We want to show it's true. The only thing we do know, okay, we know that the hyperbolic sine of x is 1/2 e to the x minus e to the negative x. That's all we know, right? That's all we know. And so what we need to do is somehow get from there to there. So we're going to do something we haven't done. I'm going to put y'all in breakout rooms in groups of 4. I'm going to let y'all talk amongst each other and see if any groups can come up with a way to go about trying to get from the black to the red. All right. And this is more of just trying to formulate a plan. I don't want you to try and work through it because I'm not going to give y'all enough time to work through it. This problem's going to take us a little while. So let's just try this breakout room thing. You're going to be invited to a room and then just go in there and meet your classmates. And what do y'all want? 3 to 4 people or 4 to 5? Doesn't matter. I'll go 3 to 4. Let's see what happens. And I'm going to put y'all in there. I'm going to let y'all think. I'm not going to go, if y'all have a question or something, there is a way when you're in these rooms to like raise your hands to ask me a question. I'm not going to answer any questions. I truly just want to leave y'all in the room for like, I don't know, let's just do 10 minutes. I'm just to see if anyone can come up with a plan. Any groups can come up with a plan, all right? And then what'll happen is you'll get an invitation to come back to the room, back to here, okay? Here it comes. Go have fun.
Oh, sir.
Yes, sir.
My computer froze right when you sent us to the breakout rooms, and it said to
Okay,
retry.
here we go. Yeah, I'm just gonna send you, let me
Thank
see
you.
it. Let me see. Does that work?
No, I haven't got any invitation yet.
Okay, hold on. It's not showing you here.
Yeah, right when you sent it, it said retry and select, so it just froze. It always freezes on me real quick.
Huh, I'm not getting an option to send you there. Hold on, let me try something. Try and reload my breakout rooms. It says that I have you in breakout room 1, but you
Yes,
haven't
I got an
joined.
invitation right now. I just got one right now. Thank you.
Okay, good. There we go. Another 30 seconds, everyone will be back here. Okay, so because it's already 10 after 12, we're gonna have to move quickly here. I'd love to sit here and talk to each, have a representative from each group kind of tell me what they were thinking. But in an effort to save some time, let me just kind of guide us through this. First, you have to know from college algebra how it is we go about finding the inverse of a function. So if we're given a function, to find the inverse, what we do, and see if this looks familiar, is you rewrite it, but everywhere you see an x, you put a y, and everywhere you see a y, you put an x. And then after you do that, you solve for y. So this example, what I did here was, here's y equals some function of x, and we want to find the inverse of it. So first thing we do is everywhere we see an x, we make it a y, and everywhere we see a y, we make it an x. And then you take that equation and you solve it for y. And so you algebraically, I'm just gonna, I just add 2 to both sides, and then after that I divide both sides by 5, and you get this. And that is the inverse. To see that, I showed a little example here. If you have input, output, let's say we take the number 3 and we plug it into the original function, 5x minus 2. So 3 times 5 is 15, take away 2, it's gonna spit out 13. Now, if we take 13 and plug it into what we said the inverse was, 13 plus 2 is 15, divide that by 5, you get the 3 back. So that just shows you that it works, okay? So that's what we have to do in this problem. We have to switch x and y, and then solve for y. So did any groups get that part? Yeah, I see a couple of nods and of yes there. I mean, if you didn't, that's okay. I just wanted to see if anyone had. So let's take this right here. I'm going to start this on a new page. And let's try to see if we can't switch the x's and y's. So what we're going to do is I'm going to erase this. I'm going to call this y. So that's our original function. That's our hyperbolic sine function. And now we're going to switch x and y. So I'm going to say x equals 1/2 e to the y minus e to the negative y, and now solve for y. So any recommendations on how I could solve for y here? I need to get y by itself.
Can you start by multiplying times 2, both sides?
Let's multiply both sides by 2, okay. All right, that's good because that kind of frees up. We don't really need the parentheses anymore. All right, here's the hard part. So a lot of times students will say, well, let's just use the natural log because the natural log will undo the e. But let me show you why it won't work. We can take the natural log on the left. That's not a problem. But when you go to take the natural log on the right, you have to take the natural log of the whole side. And the problem is natural log doesn't distribute through parentheses. You're doing natural log of this, and this right here is subtraction, and there's no way to split that into 2 logs or do anything. And it doesn't just kill off each of them individually. What you'd have to remember from college algebra is we have a rule that says this: the natural log of x times y is natural log of x plus natural log of y, and then we have another one that says natural log of x divided by y is natural log of x minus natural log of y. These were our condensing and expanding formulas for logs, but we don't have any formulas that allow us to take a sum inside of a log and turn it into anything, or to take a difference inside of a log and turn it into anything. These formulas, there are none, okay? So there's nothing I can do with this, all right? So that step won't work. So what you have to do instead, and this is why I like showing this example, because we're going to wind up doing something that most of you have never seen before. I'm just going to, let me just rewrite it, and then I'm just going to take you on this journey with me here. I'm going to write that as this. E to the negative y is the same as 1 over e to the y. I'm going to multiply both sides of the equation by e to the y to clear the fractions. So I'm going to multiply the left side by e to the y. And I'm going to multiply the right side by e to the y. So just remember, I'm doing e to the y here, e to the y here. When I multiply e to the y times e to the y, I get e to the 2y. And then I get minus 1 because I just get e to the y over e to the y. And you may be looking at that going, okay, is that any better? Well, we could, maybe you could say, take the plus 1 to the other side, right? You could do that. Or add 1 to both sides, right? Okay, but I'm gonna do it a little different. Here's what I'm gonna do. See if you follow this. So what I decided to do was move everything to the right side of the equation. Everything went to the right, but then I actually kind of switched it and made the 0 be on the right instead of the left. Okay, so I just really moved this guy over here, which made it negative, made this side a 0, but then I just rewrote it. So is everyone comfortable with that? I'm going to do one more thing. Now, I recognize that that e to the 2y is actually the same as e to the y squared. Now, this is an important step because if you squint your eyes just enough, you can imagine making a quick little substitution. U is e to the y. And if you do that, it becomes u squared minus 2x times u minus 1 equals 0. Now that looks a lot like a quadratic, doesn't it? Doesn't that look kind of like, it's not exactly, but kind of like this, like a x squared plus bx plus c equals 0. It's kind of like that, but instead of x, we have u, right? And in the past, when we've used a quadratic formula in the past, haven't a, b, and c always just been numbers? And the variable x has been our, been the variable. So here, a would be 1, right? C would be -1. But what would b be? What would b be?
2x.
Yeah, it would be the -2x. See, it's not a it's not a constant, it's actually a variable. So we kind of have like a u squared plus b times u plus c equals 0. And I don't think we've ever really dealt with this in college algebra where we look at something as being a quadratic where the coefficients aren't numbers. Here we have a coefficient that's a variable, but we can still apply the quadratic formula. So the quadratic formula says that, let me write the quadratic formula down over here. The quadratic formula says that if you have a quadratic equation in this form, the solutions are x equals -b plus or minus the square root b squared minus 4ac all over 2a. So hopefully we're all familiar with that. So that's what I'm going to do here. But instead of x equals, I'm going to put u equals. And now I'm going to start writing this down. What for us is -b in the formula?
2x.
It's positive 2x plus or minus square root. Oh. Okay, b squared. What's b squared for us? So we're squaring the, so a is that, b is that, c is that. So we're squaring -2x, aren't we? So we get 4x squared. Does anyone have any questions what I'm doing? Minus 4 times a, what's a? A is 1, right? And c is -1. And then all of this over 2 times a, which is 1. Remember, we're trying to get, at the end of all of this, we're trying to solve for y, right? Right now, we don't even have y here. We just have u's and x's. But I'm going to clean this up. U is equal to, let's see, 2x plus or minus square root. This becomes 4x squared plus 4 over 2. Any questions there? Do y'all see this 4 that's here and here? Can we factor that out of both those terms? And then can we pull that out of the root as a 2? Okay, so I'm going to do that all in one step. The 4s are going to come out, and it's going to come out of the root as a 2. And that allows me to reduce all of these by 2. So that gives me now u is equal to just x plus or minus square root of x squared plus 1. And then I don't have a fraction anymore, right? Now, what was u? What was u?
E to the y.
E to the y. Okay, so let's substitute that back in. E to the y equals x plus or minus the square root of x squared plus 1. Now you can take natural log on both sides because you have e to the y by itself, right? You have it as a single factor. So now if I take natural log on the left and natural log of everything on the right, the natural log and e kill each other off, you get y equals natural log of x plus or minus the square root of x squared plus 1. And is that the formula? Let's look back up here. Right here. Right, we were trying to show that that was true. Is that it? What's different about the formula? There's something different.
It's got the minus in there.
Yeah, ours has a plus or minus. So, but the answer has only a plus. So here's the reason why we're going to throw the minus away. Does everybody agree that you can't plug a negative into a natural log? Right? You can't do that. It's not allowed. It's not in the domain. Now, do you all agree that x squared plus 1, do you all agree that that is bigger than just x squared? Sorry, square root of x squared? Right? Taking the square root of x squared plus 1, well, x squared plus 1 is definitely bigger than just x squared. So this thing is bigger than x squared, but that's just x, right? Well, we could say absolute value, but doesn't matter. This, what I'm saying is this piece right here is bigger than the absolute value of x. So if I take x and I subtract the absolute value of x from it, wouldn't that be I mean, sorry, this number is a little bigger, right? This is bigger than this. Right, so this right here is bigger than that. I'm going to get a negative number, is what I'm getting at. And so I can't have that, so I throw away the negative, the minus. Okay, that's it. The whole point of that little exercise was to show you that sometimes the quadratic formula can be used in places that you didn't think you could normally use it. If your coefficients are variables, you can still use the formula. All right, now, there are 6 inverse hyperbolic trig functions. I've only shown you the formulas for 3 of them. The rest are actually in the book, but they're not important. We're not going to be using them. But here they are. I'm not going to go through each of these. And then we have 6 derivatives, and I'm not going to go through the derivatives of these. I could right now take the derivative of this, and that would be chain rule, wouldn't it? I'd take derivative natural log of something, which would be 1 over the something, then I'd take derivative of what's inside, and that would be, you know, some chain rule in there and stuff. All you need to know is that there are 6 derivatives and where they are in your formula sheets. So if I go back to the formula sheets here, look at this. This page right here kind of summarizes everything. You've got your 6 trig functions from pre-cal and their derivatives. You've got your 6 inverse trig functions and their derivatives. You've got your 6 hyperbolic trig functions and their derivatives. And you've got your 6 inverse hyperbolic trig functions and their derivatives. All right, here they are.
They look the same as the regular inverse, except for the
One thing to be careful of, sometimes this happens, you'll be looking at the table and you'll be looking for like this one. You'll be looking for the inverse sine derivative and you accidentally look at this one. Just that little h in there, right, throws it off. So just be careful. Any questions? All right, so that's it. That is it for all the different derivatives that we need to know. We are pretty, oh, whoa, I don't have no idea what I just did. Shit. Hold on a second, I accidentally killed my little. Okay, there we go. We are pretty much done, okay, with reviewing, or not reviewing, but you know, it's kind of like we have a toolbox of functions that we've learned in our lives, right? College algebra, pre-cal. Now what we've done in Cal 2 is we started the course by adding these additional trig functions, hyperbolic ones and their derivatives to our toolbox. And so now we're ready to get into what Cal 2 is about, which is really starting out with antiderivatives. All right, so let's go ahead, and we don't have a whole lot of time, 15 minutes. I think I'm going to be able to get a lot more done in 15 minutes than you might think. All right. So these notes, again, these are all online. First note, a function f is called an antiderivative of little f on an interval I if the derivative of capital F is equal to little f for all x in the interval I. So this is just a definition of what an antiderivative is. We will say that a function is an antiderivative of some other function if when you take the derivative of it, you get the original function. So as an example, try to move this over. So as an example, if I say capital F of x is equal to I'm trying to think here how I want to do this. X cubed and little f of x is equal to 3x squared, then what we can say is that this guy right up here, this is called the antiderivative of 3x squared, okay? Why is it the antiderivative of it? Because when you take its derivative, you get 3x squared. We touched on this, and I know a lot of you came over from Cal 1, y'all talked about this already. Is that the only antiderivative of 3x squared? Is there another one? Could I have a different capital F of x that would also be an antiderivative of this 3x squared? Someone give me an example. Any function that when you take derivative of it, you get 3x squared.
You could just add a constant to it, right? Like
Yeah, okay, so x cubed plus 4, right? That would also work, because when I take derivative of that, I get 3x squared. And I could sit here and do this all day long, right? X cubed, I could subtract 10 from it, and I'd still get 3x squared if I took the derivative. Now, could I do this? Could I do like x cubed plus x? Would that work? No, that wouldn't work because the derivative of x is 1. And that wouldn't be 3x squared. It'd be 3x squared plus 1. So that wouldn't work. This actually has to be a constant, doesn't it? That has to be an actual number, a constant. If it's anything other than number, it's not going to work. But this right here is like a general format of what all the antiderivatives of 3x squared look like. And so that's what the next note says. It says if f is an antiderivative of little f, then f of x plus c is the most general antiderivative of little f. So we call this right here, we call that the general form of the antiderivative because it covers all the different constants. So this first example I gave here in yellow, that is a specific example of an antiderivative, but the green is the general form of the antiderivative. So all antiderivatives must look like that. And what you should notice right away is that, like in Cal 1, when we think in Cal 1, you were given a function and you were asked to take the derivative, right? And your answer was a function. What we're saying here is that if I give you a function and we want to talk about its antiderivative, we're actually getting an infinite number of answers, aren't we? An infinite number of functions. But they all have something in common, right? The only difference between them is a plus c. And we learned in college algebra that when you take a function and you add a number to it or subtract a number to it, graphically, all that does is shifts our graph up and down. So you can see this from this visualization here. If you take a look at the function 2x, now I didn't do that one over here, but if we were to have started out with a little f of x, and I say that's 2x, and I say find an antiderivative of that, you would say, okay, one antiderivative of that is x squared. And then someone else would say, hey, another antiderivative of that could be x squared plus 1, and then x squared minus 4, and x, all these different things, right? The general antiderivative would be this. Right, that's our general. So this right here, all these antiderivatives create a family of functions. So what I've done here is I've graphed here in red the 2x, that's the little f. And then the blue one is actually a specific example of an antiderivative of that. And I could move that graph up and down, and any of those would qualify, right? So if I kind of plot a few of them, there's a few of them, here's a few more of them, I could have more, and even more. All of those parabolas are antiderivatives of the red one. And wow, it's weird. Does this red line not look straight to y'all anymore? Isn't that weird? No, to me, it doesn't look straight anymore. It's an illusion. Huh, that's strange. Okay. So all of these black curves here come from the family of antiderivatives. And what they all have in common is that if you look at the slope of the tangent line at any point, they're identical. So I've got, see those little short little tangents I've got there? All of those, notice they're parallel all the time, no matter which function you're on. So that's why the derivative of any group from that family is always 2x, because the slopes of the tangent lines are always the same. And we could do this for any function. So here's another example. The red one is the little f, and then the blue one is the capital F. And we can have an entire family of those capital F's. And again, they all have that property that the slope of the tangent line is the same in that family. At any point of x, any value of x, go up or down anywhere on any of those curves, and they're all going to have the same slope. Okay. Now, what are the things we need to know? Coming in just day one on antiderivatives, what are the things we need to know going backwards, right? Because that's really what we're trying to do here. So these are things that you should have known what their derivatives were in Cal 1, and so now going backwards, the antiderivative should be obvious. So the antiderivative, come on, oh, what did I do? Okay, the antiderivative of 1 over x, so if this is our function, the antiderivative of that would be natural log of x. Now, plus c would be the general form, right? The antiderivative of e to the x is itself plus c. The antiderivative of cosine, you have to be careful, antiderivative of cosine is sine. Why? Because the derivative of sine is cosine. What is the antiderivative of sine, though? This one is the tricky one. The antiderivative of sine is negative cosine, and the reason, plus c, the reason is this can't be just cosine, right? Because if you take derivative cosine, you get negative sine. So what you have to do is throw a negative in front of it, and then when you take its derivative, the double negatives will turn into the positive sign. You should also know the antiderivative of secant squared, because you know from Cal 1 that the derivative of tangent is secant squared. You should know the antiderivative of secant tangent, because from Cal 1 you know the derivative of secant is secant tangent. And then this one we learned last class, the antiderivative of 1 over the square root of 1 minus x squared is arc sine. This is the one I put the 5 stars on, right? Like, or a bunch of stars. I said, remember this one, remember this one. The antiderivative of 1 over 1 plus x squared is arc tangent of x. Antiderivative cosine hyperbolic is sine hyperbolic. Antiderivative sine hyperbolic is cosine hyperbolic. So basically anything that we kind of knew from Cal 1, you should now know backwards. So let's practice. Let's do a couple of problems now. We're running out of time. So this first one here, we have little f of x. But you know what? Before we get to this example, let's do something. Let's say that we have x to some power n, and we want to know the antiderivative. Not the derivative, the antiderivative, right? Well, what do we know about this from Cal 1? We know that when we take derivatives, so this is the thing we're going to take a derivative, x to some power, right? What happens to the power when you take the derivative? When you take a derivative in Cal 1, if you have a power, the power comes out front, right? And you subtract 1 from the power. So if we're going backwards, what are we going to have to do to the power? Not subtract 1, but add 1, right? So we're going to need to add 1, but that wouldn't be enough. That wouldn't be enough, because if I ask you right now to take the derivative of this, right, take derivative of that, the first thing you're going to do is you're going to bring the power out front. And that power out front is going to pop out right here and become an n plus 1. And we don't want that, do we? We want that to be a 1. So what would we place out in front of this to kill off that power once it comes down?
1 over n plus 1.
Yeah, just 1 over n plus 1. And that plus c. Let me write that again a different way. So this is 1 over n plus 1 x to the n plus 1 plus c. This is the general antiderivative of any power of x. And this is known as the power rule. Now you learned the power rule in Cal 1, didn't you? But it was the power rule for derivatives. This is the power rule for antiderivatives. So as an example, if f of x is, let's say, 2/3 x to the third plus 4 root x, I'm doing this example over here, minus x root x. And we want to find the antiderivative, the general antiderivative. The general antiderivative then what we're going to need to do is we're going to need to see, first of all, that we can do these separately. There's 3 different things. They're separated by addition and subtraction, so we can do them individually. Same way with derivatives, we could do individually. When you find antiderivatives, if they're separated by addition and subtraction, you can do them alone. And then what we need to do is see if we can't rewrite these as powers of x. Like all of these have to be x to a power. This I can rewrite, square root of x can be written as x to a power, and we need to be able to rewrite that as x to a power. So let me try that first. I'm trying to get these rewritten as x to a power so I can use the power rule. So where did that 3/2 come from? Right, just rewriting those two, x to the first power times x to the half. 1 plus a half is 3/2, adding the exponents. So now that we've got this, we should be able to do this using this rule in green. We should be able to. Now, what do we do with constants? That's kind of like the question we need to discuss first. In Cal 1, when you had a constant in front of a function and you took the derivative, the constant just kind of came along, right? Just kind of followed along. Same thing with the antiderivatives. All of these constants are just going to come along for the ride. Any constants in front. So the 2/3 is coming along for the ride. Now what I need to do is I need to apply the power rule to x cubed. So in this particular expression, the n, right, the power is 3. So in the formula, I have to add 1 to the power and then put 1 over n plus 1 in front. So what goes in front? 1 over what?
4.
4, okay. And then x to the 4. And then I continue, plus, now I bring that 4 down. Now the next one, I have a half here. So in the front, I'm going to put times 1 over, so n is a half, right? And we're supposed to, in the formula, do n plus 1. So what's 1/2 plus 1? 3/2. So 1 over 3/2, x to the 3/2. And then I go to the next one, minus. Now on the last one, we have x to the 3/2. So I'm going to have to put 1 over, okay, I have to add 1 to 3/2. So 3/2 plus 1 would be 5/2. 3/2 plus 1, 3/2 plus 2 over 2 common denominator equals 5/2. Okay, so 1 over 5/2, x to the 5/2. And then this, I always am going to have to do a plus c. Oh shit, I'm out of time. Okay, this just cleans up algebraically now. Let's wrap it up for today. Finish your homework for 3-6, okay? Right? Finish your homework for 3-6. If you want to, you can start this. I know a lot of you already did this section, 4.7 in Cal 1. So when we come back next time, I'm going to just absolutely blow through this next part. I promise you it's going to go fast. And then we're going to get into, well, what's next? Chapter 5, substitution, and then we hit the real stuff. Chapter 6, that's when it begins, all right? That's when the challenge that you've heard of about this course, that's when it will begin, is when we get to chapter 6, all right? Any questions? We have a holiday a week from today, right? Labor Day holiday. All right. Okay, everyone, sorry to keep going over on time. I'll try and get myself to not do that anymore. And you can sign out whenever you want. And if you want to hang out, ask any questions, I'll hang out for a little bit. Thank you.
See you Wednesday, sir.
All right, see you.